Well, I hope you guys are having a good day. Today is Wednesday, what are we looking at? The 17th, 18th. Wednesday, the 18th. We've got a little bit more material to cover before our first exam. On Friday, we're going to wrap up new content and I'm going to talk about your exam. What I've seen, just in terms of like preparation for the exam, is I have seen that almost everyone, I think there's 7 people who have yet to do the proctorio quiz number 2, or sorry, the proctorio quiz, which is quiz number 2. And a handful of people, and some of the people who haven't done it, I'm sure, a handful of people have emailed me with like issues as to why. Um, and that quiz is up there so that you can hopefully resolve those issues. Um, I can provide you with some insight into like, hey, try using Chrome. But outside of that, sorry, I can say use Chrome, try a different browser. I have one student in my other class who reported back that Microsoft Edge worked for them. And I thought to myself, crazy, Microsoft Edge being used. Good for Microsoft Edge. Um, so, just go ahead and figure out whatever the issue is and contact ITAC and they can help you get it resolved. My technical knowledge is kind of limited. I mean, to me, since Proctorio is like an extension, that means there's probably some other extension that's blocking that from functioning, like a pop-up blocker or something like that. At any rate, that's the biggest thing on the horizon, because your exam is going to be administered on Proctorio. And I think what I'm going to do just to like accommodate as many people as possible, especially since this is the first exam, is I'm going to have it start at 8:30, and I think I'm going to probably let it be available until about, I don't know, sometime later in the day. I might just for the sake of simplicity say 8:30 a.m. until 11 p.m. I think that's what I'll do. I'll just have it be open basically all day long, with future exams kind of having a more narrow window. Um, and that's really the intent there is like exam security and everything like that. Or not everything like that. The intent there is to maintain the exam's security. Um, so with that said, I think that I have no, I'm good there. Today, what we're doing is we're building on what we did the other day. If you remember the other day, we were talking about nucleotides, nucleosides, deoxynucleosides. And now what we're going to do is take those individual nucleotides and build up into higher order structures. So one thing that you've maybe heard before, or one term you've maybe heard before, is a primary structure. Primary structure is it's a common term or a common phrase used in both protein and nucleic acid structures. Your primary structure when it comes to a DNA or an RNA molecule is basically just the sequence. Now, I want to show you on these two structures. We've got on the left-hand side a DNA molecule and on the right-hand side an RNA molecule. Now, if we look at the DNA molecule, I'm going to look at my sugar, which is right here. My sugar for a DNA molecule is deoxyribose. And so you have your 1', 2', and then our 3' carbon there. Our 2' lacks that hydroxide group. That's your clue that this is a DNA molecule. So kind of a low-hanging fruit question on an exam would be, hey, I've got these two molecules. What are they? Which one's DNA and which one's RNA? And I would expect you to look at these two molecules and say, oh, well, this right here on the left-hand side is DNA. And I actually know that for 2 reasons. One, my hydroxide group is absent on that 2' carbon. Now, can anyone add to the chat another way that I could detect that my molecule on the left is a DNA molecule? Perfect. Thymine versus uracil. This right here, this T is our nitrogenous base
Yeah.
compared to this U right here
Okay.
in um, in my RNA molecule. So that's a great distinguishing factor between these two. Um, so that's kind of your other tell or your other way of detecting the difference between these two molecules. Now, with that in mind, if you've taken a molecular biology class, some of the what we're going to talk about is a little bit of a refresher, so you get a reboot on that. But if you haven't taken one, that's okay. We'll be going through this all kind of at the same pace. Polymers are your primary structure of a DNA molecule or an RNA molecule are polymers linked by 3' to 5', or but linked sugars between 3' and 5' carbons. So here's our 3' carbon, and here's our 5' carbon. And what we have is a phosphodiester linkage or a phosphodiester bond. Now, let's go ahead and deconstruct that name. Phospho, we've got a phosphorus in the middle. And then here's an ester, here's another ester. So we've got that phosphodiester bond. Now, these two molecules, since they have this phosphate group with a negative charge there, that would indicate that that is a ion. And so we have this as a ribonucleic acid or a deoxyribonucleic acid. That's where um, that deprotonated form there is our indicator that this is an acid, or that proton has already been donated. Now, our sequence and our structure is always analyzed and always read in the 5' to 3' direction. So if I were to take this molecule right here, and I were to ask you, what is the sequence of this molecule? You would read it aloud as A, T, G, because we're going from what is our nitrogenous base on the 5' end, and then what's the next nitrogenous base, and then finally, what is the next nitrogenous base? And that nitrogenous base is on the 3' end. There's kind of an implication that you have to have this sugar, this phosphodiester linkage, this other sugar that connect those nitrogenous bases. It's kind of taken for granted when you talk about a DNA or RNA molecule, respectively. Now, in terms of genetic information, this is analogous to or very similar to the way that proteins are read, which is in the N termini to C termini end. So this is the primary structure of a protein is read N to C, and that has to do with the functional groups that make up a polypeptide or a protein. Now, if that's all new terminology, okay, that's fine. We haven't talked about that yet, so that should be new terminology. If it's been brought up in one of your other, like a molecular biology class or maybe a functional biology or a cell biology class, then that's kind of just emphasizing this as analogous information. Okay, now here's another depiction of this molecule or of a DNA or RNA molecule. Now, before you even, so whenever you see a structure like this, I think that it's best to hone in on that 2' carbon and determine, is there a hydroxide group there? Yes or no. If there is, then boom, I'm talking about an RNA molecule. You don't even have to look at the nitrogenous bases in order to determine that. So this right here is an RNA molecule. Now, with that in mind, we can translate this a couple of different ways. This is a nice little shorthand or a simplified version or a simplified model for this structure. And what we've got is our 5' phosphate going to a 3' carbon. Here's our next phosphodiester linkage, phosphodiester linkage, phosphodiester linkage. And then here is where our molecule terminates. And you'll notice that it terminates because of the fact that we have a 3' hydroxide group as opposed to what else might you see on that 3' carbon? Instead of a phosphate group, what might you see? instead of a hydroxide group, give me a thumbs up if you think that it's reasonable to see this right here. Okay. It absolutely is. Now, this is an important distinction because that hydroxide group, and this is a theme that you'll see throughout biochemistry. If you see a hydroxide group, think, I bet I could substitute that hydroxide group for a phosphate. I could get rid of that hydroxide and put a phosphate there. That's something that I want you to kind of like keep in mind as a possibility. Now, with that said, and as we continue on, if you see instead of like, let's say, so, just kind of think about if you see hydroxide and OH, you can replace that with a phosphate. If you see this right here and this right here, I want you to think about that as, okay, that's less likely to be replaced by a phosphate group. In fact, I can't put a phosphate group there. I want you to kind of, I typically don't want you to use like self-limiting beliefs and self-limiting thoughts. But in this case, I want you to look at that and see if there's a hydrogen instead of a hydroxide, then I can't replace that with a phosphate. Now I got a private message that says you can replace it with a phosphate on any prime or just 2 prime. That's a great question. Anywhere that there's a hydroxide group, you can replace that with a phosphate. Now, I say you can, but then it kind of gets into like possibility of that happening. And 3 prime is likely, or you could have a 2 prime, 3 prime cyclic phosphate or cyclic group there. But if I replaced, so okay, now I got a follow-up to that private message. So it'll change to DNA. Well, if this is a hydroxide group, as it is on the 3 prime, and then if this hydroxide on the 2 prime carbon was switched to a hydrogen, well, then that part of that molecule would effectively be like DNA. But the entire molecule, if we still have these hydroxide groups on the 2 prime carbons, it's still going to be an RNA molecule. Now, with that in mind, and you see, it is significant. So my point and the take home here is it significant to look at what is on the 2 prime and 3 prime carbons? It 100% is. On the 2 prime carbons, that can be an indicator for you to look at, am I talking about a DNA molecule or an RNA molecule? On the 3 prime, well, if I have a phosphate on the 3 prime carbon, if there's a phosphate there, then that is a molecule that basically can be continued on. It can continue adding sugars and nitrogenous bases to that. If I have a hydrogen here and here, well, then I can't add to that because I can't replace that hydrogen with a phosphate. Now, what this is going into ultimately is a way of writing these molecules in shorthand notation. So this molecule down here on the left-hand side can be denoted this way. What do you think that lowercase p right here, what do you think that indicates? Go ahead and add it to the chat or say it aloud. It's a phosphate. Okay. That's a great contribution. What else can you add? What other detail can you add about that phosphate? Perhaps where it is. On what end of the molecule will you find that? Perfect. The 5 prime end. Absolutely. So this would be an indication, or the terminology that you use is you would say that this nucleotide, or this polynucleotide is 5 prime phosphorylated. Okay. Now, my follow-up question to that is when you look at the molecule shown here on the left, and then you look at this notation right here, is this molecule phosphorylated on the 3 prime end? Go ahead and add that to the chat. And you might be thinking, oh, that's a little bit of a, you're absolutely right. No, it's not. In the event that you're looking at this and thinking like, well, it's phosphorylated on the 3' end here, and then here. Well, I would argue with that terminology, and I want you to be thinking about conventions and thinking about like biochemists, the way that people would describe this. This molecule right here, it's like a book. It has a beginning and it has an end. There's lots of stuff that goes on in the intermediate and in between there, but at the beginning, at the 5' end, it's phosphorylated. On the 3' end, it is not phosphorylated. Okay. Now, if we see this notation that I've just been writing around, this one right here, you can look at that and say, oh, well, I have to put all those lowercase p's there. I would argue that you don't. And the reason I would argue that you don't is because these lowercase p's right here, here, they don't really add a whole lot to the story. Because if you remember, when you think about the primary notation or the primary structure for nucleic acid, all that you're really concerned with and interested in is the nitrogenous bases and the sequence of those nitrogenous bases. So what is a more succinct way to note this RNA molecule sequence is to do it like this. Now, the significance of this is that you are kind of conveying and communicating, one, the sequence of the nitrogenous bases from the 5' to the 3' end, but you've included that lowercase p to emphasize that, yes, indeed, it is phosphorylated on the 5' end. And it is not phosphorylated, not on the 3' end. Now, with all that in mind, this molecule, like we looked at, was an RNA molecule. It continues to be an RNA molecule. If, however, you had a thymine and you had hydrogens here instead of these hydroxide groups on the 2' carbon, that would be a DNA molecule. Okay, so how do we denote that? Well, the way that we denote that is by putting a lowercase d and then a parentheses, followed by the sequence, and then closing that parentheses off. Because that lowercase d is significant. It does indicate you're talking about a deoxyribonucleotide, as opposed to simply a ribonucleotide or a ribonucleic acid. So this is ultimately an important part of this entire process. And it's an important thing to distinguish between these two molecules. Okay, does anyone have any questions about this? Oh, would you potentially ask a question about whether or not both ends are phosphorylated based on the abbreviated notation, or if the sequence is DNA or RNA? Absolutely. I'm happy that you asked that. I'm going to clear all my writings, and let me just show you some example questions or some examples that I might give you. If I gave you this, A, U, C, G. From that, if I said, this would be, I'm not going to ask short answer questions, but this would be a good one for me to say, select all of the statements that are true. And I would say something like 5' phosphorylated. I'm going to save time and I'm just going to write 5' phos, 3' phos, then RNA or DNA. So this would be one of those questions where I ask, like, select all of the true statements. And for this, AUCG, does that have any lowercase p's indicating phosphates? No, it does not. Okay, so it doesn't have a 5' or a 3' phosphate. So I'm going to leave those off. What do I know about this in terms of the nitrogenous bases? I've got a U there. So a U indicates that it is an RNA molecule. If it's an RNA molecule, it's not a DNA molecule. So that would be my correct answer, just selecting RNA. So then I got a private message. Is there such a is there such thing a 3' phos? Would it always be 5'? Um, no, if I were to give you this right here, ATCG lowercase p. Okay, is there a specific reason that 5' is to be subject to the phosphorylation? Well, molecules can be phosphorylated on the 3' or 5' end, or both. So, if I gave you, so let's just do a comparison to this molecule right here. I'd give you those same, select all of the true statements. DNA, RNA, 5' phos, 3' phos. Okay, so from this, you'd look at it and you'd say, okay, well, I know this end right here is my 5' end. I don't see a lowercase p there, so it's not 5' phosphorylated. I see a lowercase p right here, so it's 3' phosphorylated. Then if I look at my nitrogenous bases that make up my sequence, well, I see a T there. That's an indicator that I have a DNA molecule. So the correct pair or the correct answer options would be 3' phosphorylated and it's a DNA molecule. Is there a specific reason? Okay, yeah, I answered that. That there's no like molecules can be phosphorylated on 5' or 3' ends. Now, with that in mind, if you were to say, look at this molecule right here, PACG, lowercase p. This is doubly phosphorylated on the 5' and 3' end. And one thing that's important to know about DNA synthesis, and this is something that if you elect to take a micro or a molecular biology class, you'll get a little bit, or you'll definitely get more into this. But if I were to add this molecule to this right here, this would present a problem because what do we use the phosphates for? What are the bonds that are between the sugars, or what are the linkages? It's a phosphodiester linkage. So what we need, this right here has a 3' phosphate. What we need to add to a 3' phosphate is a 5' OH. This molecule, the second one that I've listed, has a 5' phosphate as opposed to a 5' OH, in which case it's almost like you have two things that are, I guess it's almost like you're taking two Legos and rather than fitting I usually have Legos around my office. Rather than like one end fitting directly into the other one, instead you're taking the like protruding ends of the Legos and you're putting them next to each other. And that doesn't really match up. So, there are enzymes that will act to remove this phosphate so that the addition can take place. But the point of this all, like, we're not talking about synthesizing DNA from and DNA replication. We're focused more on kind of what is the notation, what's the nomenclature for these molecules. So this would be phosphorylation at the 5' and 3' end. Okay, so now our sequence is our primary structure. Our secondary structure is what does this molecule look like? And whenever we talk about a DNA molecule, we form what's known as the double helix. Now, the cool thing about the double helix is that, there's a handful of names that should come to mind. Could anyone add to the chat maybe the person who's responsible for the X-ray crystallography that was used to solve the DNA double helix? Now, I'll give you a hint. It's not Watson and Crick. It was a woman by the name of Rosalind Franklin. And what Rosalind Franklin did was she took and developed an X-ray crystal structure or X-ray diffraction of of a DNA double helix. And the work that she did was like it was foundational work that um, Watson and Crick later used and were able to, resolve here's what the structure or hypothesize here's what the structure is and validate that. And then they were awarded the Nobel Prize for that. And, yeah, that was significant discovery. But it was really Rosalind Franklin's work that set them up tremendously. Now, if I remember correctly, by the time Watson and Crick were awarded the Nobel Prize, I think Rosalind Franklin maybe had passed away, and the Nobel Prize isn't awarded posthumously. But I think also it was just like straight up sexism. Um, and just like let's ignore the tremendous work of this woman. Um, with that in mind, Rosalind Franklin is the person who I think that you should really know their name because it's like she did the work. She did all the really foundational, important work. Now, when we talk about a DNA double helix, also, this is, we kind of take it for granted almost. But keep in mind, like people did not know. I mean, if you think about, I think it's was it the Hershey Chase experiment? It was Hershey and Chase who related genetic traits to, or found that there was something that carried genetic material. And initially it was thought, oh, well, is it protein or is it this other thing? And these nucleic acids. And I think it was Hershey and Chase who concluded that no, it was DNA, or is this DNA was the carrier of genetic material. But Linus Pauling, prior to Rosalind Franklin's work, Linus Pauling theorized that it was a triple helix. And obviously that wasn't, based on nothing. He had justification for that. But what we now know of a DNA structure is that it's a double helix. And that double helix has a sugar phosphate backbone. Now, I can ask you, and I think most people will be able to say this, what's the overall charge of a DNA molecule? And this isn't something that we're going to quantify, but what is the charge of a DNA molecule? It's negative, exactly. Now, where people kind of get mixed up is where they say, okay, well, where's that negative coming from? Well, when we look at something like this right here, that's where your negative charge is coming from. That negative charge is from the sugar phosphate backbone. Specifically, the phosphate of that sugar phosphate backbone, because that's on the exterior, that's on the periphery of the molecule. Now, the DNA double helix also has nitrogenous bases. Those nitrogenous bases are on the interior of this molecule. What I want to do is I want to focus in right here. What we have are two nitrogenous bases, G and C. And if you look closely, you can see 1, 2, 3 hydrogen bonds that are connecting G and C. If you look down here, you see A and T, and you see 1, 2 double bonds. Those hydrogen bonds are in the interior of this structure. And those hydrogen bonds basically hold those two things together. Your sugar phosphate backbone, however, is your covalent bonds that hold basically each one of those strings together. Now, the backbone is said to be anti-parallel because they go in opposite directions. And what I mean by that is if this one is 5' to 3', then this one is 5' to 3'. So they go in opposite or reciprocal directions. Now, structures of a DNA molecule, of a DNA double helix, or two major structures are the major and minor grooves. Now, these major and minor grooves are pretty significant, which we'll learn a little bit more about on Friday, because they allow for certain enzymes to basically, I always just kind of imagine that they're basically like an enzyme kind of finds its way in here and basically reads like, oh, okay, that's a G and a C, that's a G and a C. And they kind of read the sequence. They're able to like inspect it. Now, our base pairs are our A and T and G and C. When it comes to G and C, you have 3 hydrogen bonds, and A and T, you have 2 hydrogen bonds. Now, that is significant because that relates to the strength of a DNA molecule. Um, Now, I always like to think about, could anyone add to the chat? There's a technique or there's a technology known as PCR. Does anyone know what PCR is? Okay, so PCR is the polymerase chain reaction. Now, does anyone know what enzyme is involved in the polymerase chain reaction? Or what is the name of the enzyme? DNA polymerase. Does anyone know the organism that that DNA polymerase has come from? The organism is a microorganism known as Thermus aquaticus. So that Thermus aquaticus is an organism that yeah, Taq polymerase is the specific DNA polymerase that's used in PCR. Now, I bring this up because Thermus aquaticus is an organism that lives in thermal vents. It lives where there's extremely high pressures, extremely high temperatures, basically in hot springs, Hot Springs, Arkansas, but not in the like outside beautiful place. Instead, it lives in those thermal vents where the temperature is extremely high. Now, in order to survive and thrive in there, they have a genome that has a very high GC content. Um, and that GC content, if you look at, look right here and right here, you might say, oh, well, that's 2 bonds versus 3 bonds. Okay, well, that's one way to look at it. But then take it a step further. It's not just 2 bonds versus 3 bonds. If you have millions of base pairs. So if it's just 2 base pairs, okay, cool. But what if you have 10 and 6 of them? So let's do a 10 base pair molecule that is 7 G's and C's paired up and 3 A's and T's paired up. Okay. Is this, I'm going to call this A and this one B, 10 base pairs. We got 2 compared molecules, 3 GC and 7 AT. Which one of these, and add to the chat, A or B, which one of these is going to be held together, or which one is going to be stronger when it's held together? A, the GC content is what impacts that. So the higher the GC content, the more tightly that is held together. Now, this is what our GCs and ATs look like. Thymine and cytosine. We've got hydrogen bond acceptor, hydrogen bond donor, donor acceptor, donor acceptor, donor acceptor, donor acceptor. Okay, so we've got all those donor acceptor pairs for hydrogen bonds. Now, our nitrogenous bases can exist in a keto or enol form. And the reason that they do that is so that they can occupy different spaces and they can like stack a little bit better. Now, both sets of base pairs will occupy the same like latitude and longitude, the same space, sorry, the same total space. Now, with that in mind, let me clear my writing. This ATGC is known as Watson-Crick base pairing, and there's something called Chargaff's rule that basically says, oh, well, if a genome is 60% GC, then what percent AT is it? Go ahead and add to the chat. 40. Okay. Now we can take this a step further. If a genome, let's say that an organism is 25% No, I'll change from 25%. Let's say that it's 45% G. What percent A is it? Go ahead and add to the chat your percent A that this is. 5. Great. That's fantastic, because you know that if it's 45% G, it has to be 45% C. So that brings us to a total, 45 plus 45 is 90%. Okay, if it's 90% that, then all that remains is 10%. And that 10% is going to be equally divided between A and T. And so 10 divided by 2 is going to be 5% A, 5% T. So this is a type of question that I almost always ask. And that's just because with minimal information, you actually have a lot of information. And I didn't mean that to sound as like, man, I told you so, as I think my face looked there. But it's yeah, you have a lot of information before you. From your example question earlier on this slide, why are GC base pairs more powerful? Well, the reason is because you have a total of 3 hydrogen bonds between G and C, but only have 2 between A and T. And you can count those up. Here's a hydrogen bond. Here's a hydrogen bond between A and T. And then here, 1, 2, and 3 between G and C. So it's just a matter of a number, the number of them. Okay, so now when we look at a RNA molecule, RNA molecules are quite a bit different than DNA molecules, in part because typically your RNA molecules exist as single strands, as opposed to a double strand. Now, what that means is that, there's, I think, the first time I was ever like shown a, cartoon model of an RNA molecule, it was basically like this. These dashed lines here being the nitrogenous bases that aren't paired with anything. And I remember thinking to myself, like, oh, wow, it just like freely floats around. Crazy. And then I remember having trouble because I was like, okay, so if this isn't A, U, C, U, A, G, let's go with that. I know that G and C like to base pair with one another. And A and U can kind of base pair with one another. Well, why wouldn't this strand right here fold in on itself so that this G and this C can hydrogen bond with one another? And then, as I continued taking classes, it was like, well, yeah, we just show this because of the fact that RNA exists as a single strand. Can it fold back in on itself? 100%. Does it fold back in on itself? 100%. And so you have base pairing, but it's base pairing, it's intra-strand base pairing, as opposed to inter-strand base pairing. So this is one strand, 5' to 3' end. And this long strand is produced, but then it kind of like, it wraps in on itself. And it makes multiple helices. It makes also structures with different names. It makes helices, internal loops, bulges, hairpin loops. Now, there are some distinctions between a hairpin and an internal loop. A hairpin loop is basically where the loop it's kind of like a cul-de-sac almost, where, yeah, the street goes and then it just kind of circles back in on itself. Whereas an internal loop would be kind of like I'll say cul-de-sac, and then this would be like a roundabout. I'm happy that I can use traffic analogies. Roundabout. Or a traffic circle, sorry, not a traffic circle. So helices, internal loops, bulges, and hairpin loops are all structures that form in RNA molecules. Now, the significance of this is that RNA is a single-stranded nucleic acid. It likes to fold in on itself. Now, with that in mind, when you have regions of an RNA molecule that are accessible to the environment and the solution that they're in, you're going to end up with something that can hydrogen bond with everything. So that's one of the key factors in terms of the stability of RNA and DNA. So RNA is typically a very unstable molecule. So a fair question is, why do we have both RNA and DNA? Now, thinking about the differences of them, we've got our nitrogenous base differences. That's one factor. Another difference is the sugars that differ. We have ribonucleotides versus deoxyribonucleotides. Now, when you look at your deoxyribonucleotide versus oxyribonucleotide, so if this is a part of a single-stranded, so ssRNA molecule or a single-stranded molecule, and this is more typically a part of a DS molecule, well then, what's important to remember, and actually, I'm going to go back a couple of slides. I'll go to this slide right here. I'm going to clear all of this off. So this is thinking about our RNA molecule here on the left. Now, this is just a subsection of one molecule. What is, or one extremely important intramolecular interaction is known as hydrogen bonding. Now I'll ask you this question and add to the chat your answer. Can water hydrogen bond with water? Yeah, no doubt. Great. Okay. So can water hydrogen bond with an alcohol, a hydroxide group? Yes. Okay. So this right here, is that something that water could conceivably hydrogen bond with? Absolutely. You can hydrogen bond with that, hydrogen bond with that, that. These are all great candidates for hydrogen bonding with water. Now, this RNA molecule is not just in space, it's in an aqueous environment where there's a ton of water. So with all these groups being capable of hydrogen bonding, let's compare. Let's imagine instead of OH, you have H here, 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 here. Can this hydrogen bond with water? Can hydrogen, or like, let's think about if we just have a hydrogen here, then a 2' is a carbon. For a hydrogen bond to take place, what you need is you need an electronegative element like nitrogen, oxygen, or fluorine. So oxygen, we got that right there. So we have to have like oxygen, hydrogen, oxygen for a hydrogen bond to take place. If we have a carbon here, I'm going to just label that carbon as not oxygen, fluorine, or nitrogen. So this guy right here is incapable of hydrogen bonding or forming a hydrogen bond. And that's always the thing that I have to remind myself of is like hydrogen or carbon hydrogen cannot hydrogen bond. Oxygen hydrogen does it perfectly, but carbon hydrogen, no dice. Now, with that said, if you have an RNA molecule, and this guy right here can hydrogen bond with water. We're not talking about a single water molecule in a vacuum. Instead, we're talking about, well, billions upon trillions of water molecules, in which case this guy can kind of be pulled off with these molecules. This hydroxide group can have forces pulling it this way. This can have them pulling in the opposite directions. In which case, if these hydroxide groups are kind of pulled in different directions, that's going to put strain and stress on this bond and this bond, on our molecule as a whole. It's almost like it's this molecule is being pulled in different directions, stressing it and ultimately leading to hydrolysis. So if we compare an RNA, a single-stranded RNA molecule, it's susceptible to so many different hydrogen bonding sources. And that's not even mentioning that this can hydrogen bond, and this can hydrogen bond, and this can hydrogen bond. There's basically a single-stranded nucleic acid is being pulled in 4 different directions at any given point in time. Now, when we talk about a DNA molecule, you don't have that hydroxide group. In addition to that, your nitrogenous bases, those are hydrogen bonding with other nitrogenous bases. And so the sources for stress and strain are so much lower when we talk about a DNA molecule. So when you ask the question, why do we have DNA and RNA? Well, DNA is like a long-term storage molecule. And so it can preserve things by having that hydroxide group or not having that hydroxide group. In the case of ribonucleotides, by having that 2' OH group, you have a molecule that's much more susceptible to hydrolysis, whereas in DNA molecule, you lack that 2' hydroxide group, so it's much less likely to hydrolyze. So essentially you have RNA, which can go to, it's like a temporary or transient molecule. It can go to the ribosomes and lead to the production of a protein, but it's not expected to exist in perpetuity, and it's not expected to exist for forever. Instead, it's just there. It's like, I've made it, or I've made my mRNA, and then I can go to the ribosome so I can make my protein. And it's almost like, yeah, I might have $1,000 in my bank account. I've got $25 in my wallet. Which one of those sources of money is more stable? Which one of them is more likely to be spent or lost? Well, the money that's in your wallet, because you don't know, you might accidentally pull your wallet out of your pocket and your wallet falls, and then you've lost it. So is DNA more stable but less likely to hydrolyze? Well, I'm going to rephrase that question. This is a private message. DNA is more stable because it is less likely to hydrolyze. So don't use the word but, because that kind of says like it's a contrasting thing. It's because it's lack of hydrolyzability that makes DNA much more stable. Okay, well, that's where I wanted to end, and you got about 1.5 minutes left. So I'm going to go ahead and stop my recording.